Okay, good morning, everyone. Today I'm going to try and wrap up chapter 3, and then Friday we'll begin chapter 4, transient. So today we will look at the last remaining topic of the capacitors and then example problems. Where is, okay, there it is. So if we have a fully charged capacitor and we take it out of a circuit, it has stored energy. We can measure the voltage across it, right? Last class, we talked about charging a capacitor, and we saw how electrons are moving in the circuit will accumulate charge on either side of the capacitor, which can be measured as capacitor voltage. So when you remove the capacitor from the circuit, that capacitor voltage for an ideal capacitor will stay indefinitely, right? Again, ideal capacitor, ideal inductors, it's just hypothetical, theoretical, right? But in real life, what will happen is these capacitors will slowly discharge through its internal resistance. So if we take a real life capacitor that has charged and stored energy, that insulator, the insulating material between the two plates is not ideal, right? A real life capacitor, nothing is ideal. And so it will slowly discharge through this insulating material. It'll slowly discharge to that insulating material. So if you take a real life capacitor, charge it, remove it from the circuit, after a certain point in time, all of that charge will be completely dissipated. All of that energy will be completely gone. And we can represent that as a resistor in parallel with that capacitor. An inductor, we represent it as a resistor in series with that inductor. For a capacitor, we can model that resistance as in parallel. Again, it's very infinite, very high value, right? Ideal capacitors, that resist ideal capacitors, that value of the resistor is infinite. Real life, it's mega ohms or higher, very, very high, depending on the construction of the capacitor. Now, capacitors and inductors can only store and release energy, right? Intake energy, store it, and then release it back into the circuit at a certain point in time. Going off on a little bit of tangent, if you take a real life capacitor, what happens if you short the two ends of that charged capacitor? You have stored energy, it's like a battery, and you take two ends of the battery and you short out the terminals, meaning you connect a wire from the positive to the negative terminal. What will happen? What is the resistance of a short circuit wire? It's 0, right? So if R is 0, I is infinite, meaning all of that energy is being released all at once. In a capacitor, most real life capacitors are very small. So the charge and the voltage they store is also very small. So you could, I wouldn't want to use the word safely, but you could take a capacitor out and short the two leads and you'd see a small spark. If it's a large capacitor with a large amount of stored energy, you might see a bigger spark or even an explosion. If you take a battery, a coin cell battery or a 1.5 volt battery, you always hear the warnings, right? Never store batteries with some metallic objects like keys or coins or something like that. It's to prevent the inadvertent shorting out of those terminals. If you take a wire and you connect the two ends of a battery together, it won't explode immediately. What will happen is that energy will be released all at once. But in a capacitor, the stored energy is limited, right? one spark and the energy is gone. A battery is also limited and finite, but it is far larger than just a capacitor. So battery will keep supplying that infinite current for a long period of time until the entire charge is depleted. But before that charge gets depleted, it overheats, and you have Samsung Galaxy Note 7. I was a big fan of the Note series. That was like one of the best phone series. But if you have ever, I don't know if you all remember that, but a few years ago, Samsung came out with a Samsung Note 7, and apparently the people or the team who designed the batteries, in the pursuit of making the phones thinner and thinner, made the battery very thin. So the walls between each of the cells inside the battery were very, very small and thin. That shorted out the individual cells, the positive and the negative terminal. So all of that energy was being released all at once. And so if you leave it for a long period of time, which of course it's internal, so we are not actually, there's no way to disconnect it, right? There's no way to disconnect it. And so, phone is just sitting there, charge is accumulated, it's now releasing, it's overheating, and the energy is still not dissipated. At some point, it overheats so much that it explodes. And so that's what happens. That's also what happens if you use a charger. So that's the reason why some manufacturers always tell you, do not use a charger that is not approved. But what they're saying is, every charger nowadays, even cheap ones that you buy off the shelf, like no name, no brand ones, will have some internal circuitry. The charger has the capacity to supply a whole amount of energy from the wall. But your devices, when they charge, they tell the charger, okay, I'm full now, stop sending power. If the charger doesn't stop it, then it'll keep sending power even if the battery is completely full. And so if the charge is coming into the battery, they are receiving more and more energy, the battery swells up, and then your device explodes. That's the reason why the manufacturers tell you. Well, that's one of the reasons, but they use that as an excuse to sell more expensive chargers of their own. Anyway, coming back to our topic. Capacitance is measured in the amount of charge that can be stored, right? So mathematically, we can describe the value of capacitance C as the ratio of the charge that is stored for every unit voltage that is applied. So 1 farad is 1 coulomb of charge stored for 1 volt applied voltage. C equals Q over V. We rearrange the terms and we can obtain Q is equal to CV, which is what we will use to derive the capacitor current equation. Q is equal to CV. Okay, Q is equal to CV. Now, just some small examples that I want to quickly go over, just to show you how the value of the capacitance can change, depending on the amount of voltage applied and the amount of charge that is stored. So if you look at example A, you're applying 2 volts across the 2 plates and storing 6 coulombs of charge. So for a specific amount of voltage that is applied and the amount of charge you wish to store, you need 3 farads of capacitance, for example, A. Oh, who is farad named after, by the way? I've stated this before. Michael Faraday, yes. Nobody in the first section answered. All right, so the second one, exactly the same thing, same voltage being applied, 2 volts being applied, but you want to store more charge, then you have to build a larger capacitor. 6 farads, twice as much. Okay. And when I say build a large capacitor, we will see on the next slide, on the next page, the physical construction of a capacitor and how it can be, and how the equation relates those physical dimensions. And then C, example C, same charge as B, 12 coulombs, but now we increase the voltage from 2 to 8 volts. So when it goes from 2 to 8 volts, the amount of capacitance required is only 1.5. 25% of example B, right? From 6 to 1.5. It's even smaller than the first example A, simply by increasing the amount of voltage handling capacity. So let's look at a physical construction of a capacitor. Two parallel plates separated by an insulating material. So the separation determines the capacitance value. Remember, I said two hands put together separated by air is a capacitance. The value is very small. Obviously, the far apart they are, capacitance will be very, very small. When you bring it together, it will still be small, but maybe with special tools, we might be able to measure it. So it's inversely proportional. C, the physical value of the physical capacitor, is epsilon A over D. D is the distance between the two plates. So the smaller the distance, the higher the capacitance. And then the A represents the cross-sectional area of the plates. Cross-sectional area of those plates. Okay. Epsilon is the permittivity, and it's a product of epsilon 0 and epsilon r. If you think back to the inductor equation, you had mu, the permeability, which was the product of mu 0 times mu r. This is epsilon 0 times epsilon r. Very similar. Epsilon 0 is a constant, right? It's a constant. It is the permittivity of vacuum. Epsilon r is a material property, meaning the material that is used as the insulator. Okay, that's the separation. And so it's a material property relative to epsilon 0. So now I'd like to expand a little bit on the cross-sectional area. If the plates are not of similar dimensions, which area would you take? Yes. That was also one of the answers in the previous section. Smaller area. That is correct, but not quite. Not quite the entire answer. Think of it in terms of the definition of the capacitor. What does capacitor require? Is this capacitance one plate? Is this two plates? So it requires two plates, right? So if it's two different dimensions, and in this case, again, a picture is worth 1,000 words. Light bulbs going off or going on, right? Where is the capacitance? Just the overlapping part, because that overlapping part is the only place where you have two plates. Everywhere else, it's single, right? Outside of that overlap, it's a single plate. The overlap is the only portion where you have two plates. So the cross-sectional area, in general terms, it says it's the area of the plate or the area of the plate, because most capacitors are constructed with the exact same dimensions of the two plates. But in real life, there are many cases where you have overlap between two conductors separated by an insulating material, and that would be the area of that capacitor. Okay, equations. We looked at the primary equation, Q is equal to CV. Q is charge. Electrical current is the rate of flow of charge. So dQ over dt. If you take the derivative of both sides, C is a constant, comes outside. You get dQ over dt is equal to C dV over dt. dQ over dt is nothing but I. And so you get the primary current equation. I is C dV over dt. That's the primary equation. For a inductor, it was L di over dt. Inductor voltage is equal to L times di over dt. Exactly the same equation, but similar structure, but the quantities are flipped. Capacitor current I is C times dV over dt. And if you notice here, the notations I'm using are different, but they mean exactly the same thing. For an inductor, I pointed out that sometimes we use the notation as a function of time. We might use a subscript L and C, right? And so these are on purpose. I wanted to show that the equations are exactly the same, whether it's simple I or I of t or IC or IC of t, they all mean exactly the same thing. So if you're in a meeting or if you're reading a technical report and it states I of t and the next page it might just say I or V, well, just know that it is a function of time. Sometimes the answer could be constant, meaning the value doesn't change. We'll look at that in one of the examples. And then other times you might see an expression which gives you as a function of time. We already looked at this slide. Capacitor voltage, again, we have the standard expression I is C dV over dt. We simply take integral of both sides. We integrate both sides and you obtain capacitor voltage as integral of the current. That's it. V is 1 over C integral of the current. Don't worry about the derivation. Don't worry about anything else. We'll look at it in detail when we actually get to the examples. Power equation is still standard. P is the product of the voltage and the current. So P of t is V of t times I of t. Power as a function of time, product of the voltage and current, which are functions of time. You plug in the values, CV dV over dt. Energy for a capacitor is half CV square. For an inductor, it was L half Li square. Again, remember, for an inductor, we think in terms of, or we express in terms of the inductor current. Capacitor is the voltage. So for inductor, it was half Li square. For capacitor, is half CV square. Okay. For examples to cover, at this point, these examples are less about circuit analysis and more about just math. Okay. So it's less about circuit analysis, more about just math. And all of these examples apply equally to capacitors and inductors. Okay. So if we look at the first example, what are we given? We are given the values of the capacitor C. We are given the voltage that is being applied to that capacitor. And we are asked to calculate the current. That's it. Right? CV and I. So what do we have? We have the standard expression, right? I is C dV over dt. Capacitor current I is a product of the capacitance and dV over dt. Plug in the values, perform the calculation, you'd have your answer. So C is 5 microfarads, 5 into 10 raised to minus 6. And voltage is 10 cos of 6000 T. What is the answer? You all solve this and then I'll give you the answer. Anyone? Anyone online solve this? What is the derivative of cos x? Minus sin x, right? One of the two basic functions that we look at very early on in trigonometry. Sin x is cos x is minus sin x. Constant, so we have cos of ax. Constant comes outside. So you got 5 into 10 raised to minus 6 times 6,000 times 10 sine of 6,000 t. And then we have the minus sign. So let's put a minus right at the front. Solve that and you obtain the value for the current as minus 0.3 sine of 6,000 t amps. Never forget the units. Even though it's a function of time, the quantity is still current, and so the answer, I mean, the unit should still be amps. Okay. As I said, it's less about circuit analysis and more about just math. Now note, as stated, right? I stated earlier that all of the examples can apply equally to capacitors and inductors. So if this problem was with regards to an inductor, it might look something like this. Inductor value would be given to you, let's say 5 millihenry or 50 millihenry. Current I would be given, let's say 10 cos 6,000 t. And inductor voltage would be asked to be calculated. Simply plug in the equation. V is equal to L d.I.O. dt and solve. Right. So the process, the method applies equally to inductor as well as capacitor. In the first example, we are given capacitor voltage and we're asked to find current. The same example for an inductor would look like, well, like how I've written down, meaning the inductor current would be given to us and we'd be asked to find the voltage. Make sense? All right, any questions? Okay, example 2. This time we are given the current, we are asked to find the voltage. So instead of taking the derivative, we will now integrate. So I of t is given to us. We are asked to find the voltage. Capacitor voltage is 1 over C integral T0 to T times I. There's also another term that comes after, which is voltage, initially stored voltage at time t equal to 0. For now, this value has, this is a value of 0 volts. This is initial stored energy. And I will talk about this in example 4. Okay. Capacitor voltage is 1 over C, 1 over 2 microfarads. Integral T0 to T. And it's milliamps. So dot dt. Okay, constants and everything comes outside. So you got 6 into 10 raised to minus 3 that comes out. Divided by 2, so that becomes 3. And let's see what I have. Minus 3000 T, so minus and e raised to minus 3000 T. Zero to T. Now to explain the limits of the integral, okay? So we have 6, we have 10 raised to minus 3. Constants come outside. So 6 into 10 raised to minus 3 divided by 2 into 10 raised to minus 6 gives you 3000. You got e raised to minus ax. So that also comes outside. Now, integral of e will be e. Limits is t0 to t. T0 is the point in time which we begin analysis. Nothing is given to us, we'll simply take it as 0. So the moment in time when we begin analysis is 0. So T0 is 0. The end time is also not given to us. So since nothing is given to us, we simply determine the voltage as a function of time. So the end of the limit, or the end of the integral, is simply the variable t. That's what it is. That's the explanation for that. Hence the limits of the integral going from 0 to t. Since no fixed time period is given to us, we will determine the voltage, we'll determine the value as a function of time. And because it's going to be a function of time, we plug in the end of the limits as variable t. And that's it. We solve that. And you plug those values in. This, of course, because minus 1, this becomes, excuse me. So in this case, the variable under integration is t and the limit is also t. So you plugged it in, you got e raised to minus 3000 t minus e raised to 0. We can solve that one more step. It's 1 minus e raised to minus 3000 t volts. Does that make sense to everyone? Hopefully. Any questions before I move on to example 3? Okay. So this is a technique called piecewise linear analysis or linear piecewise technique. In this case, we are given the graphical description of the voltage. Time is on the x-axis. So usually any problem that you look at in EE, especially in this class, you always have time on the x-axis. And voltage is given to us v of t, function of time. If we want to solve this mathematically, we need to describe this function, this graphical description in mathematical terms as a mathematical equation. But there is no way to do that unless we divide this function into multiple separate pieces. And each piece will then have a linear relationship with time. And hence the technique is known as piecewise linear analysis. linear pieces with respect to time. So if we break this up into 2 time periods, all this T1, all this T2, you can see each one of those pieces is a straight line, right? It's a straight line. And we will use the slope line intercept method to describe that line. So we'll find the slope, then we'll describe. We actually don't have to describe the line, and I'll tell you why. And actually, you will tell me why. Same equation of a line. Different people use different variables sometimes to describe this, but it means exactly the same thing. Y-axis, we have time. X-axis, we have voltage V. B is the y-intercept. What is M? Slope, right? Slope of the line. What is the line describing? The line is describing voltage as a function of time. So if you take the slope of that line, what is it that we are determining? dV over dt. So M is dV over dt. If we find the slope of the line, we can straight away find the current by simply multiplying with the capacitance. That's it. I is C dV over dt, so it becomes I is equal to M times C. Or actually, let me write it down this way. M comes afterwards, so C times M, where M is the slope of the line, dV over dt. And that's one of the beauty of this technique. All right, so the first one, slope of the line, can be given by any two coordinates, y2 minus y1 divided by x2 minus x1. I typically always take the two endpoints. And so for T1, M1 would be equal to two endpoints gives me 24 volts minus 0 volts divided by 6 milliseconds minus 0 milliseconds. That gives me 4 or 10 raised to minus 3. So 4,000 volts per second or 4 volts per millisecond. Either case is right. And therefore, my current I is simply C times I1, or sorry, M1 this gives me a value of 20 milliamps. One step answer. All right, let's take a pause. Think on that. Let me know if you have any questions. Any questions at all? Anyone? Yes. Yeah. Capacitor. Second time period, we do the exact same thing. We can find the slope of the line M2 by using the two endpoints. So this time it will be 0 volts minus 24 volts divided by 8 milliseconds minus 6 milliseconds. Ten raised to minus 3, which is minus 12 volts. per milliseconds, or minus 12,000 volts per second. Therefore, I2 is C times M2, which gives me a value of minus 60 milliamps. Minus 60 milliamps. Note that the current I is not a function of time. The answer is simply a constant value. If it's a constant value, then between the values of 0 and 6, it's a straight line of 20 milliamps. And between 6 and 8, it is a straight line of minus 60 milliamps. And hence the plot as shown in the figure. All right. So this example as applied to a capacitor would probably give you, not probably, would give you a inductor as a function of time, and then ask you to find the voltage for the inductor. So you would just break it up into two pieces. V equals L di over dt. You do the exact same thing, find the slope of the current, multiplied with the inductance, that would give you the inductor voltage. Same approach, no difference. But now let's look at the other side, meaning if you're given the capacitor current and we are asked to find the voltage, meaning we now have to perform an integration. Same approach for piecewise linear analysis, and I have about 14 minutes left, so I'm going to go a little bit faster on this one. The values are not quite evident from the graph, but I will tell you this is 16 microamps. And this one at the bottom is minus 8. Minus 8. T1 and T2. T1 is from 0 to 2, and T2 is from 2 to 4. Now, here's the time where we take the initial stored energy into account. Okay. And of course, I have to describe the equation of the line right now because I need to integrate. So for T1, M1 is 16 minus 0 microamps divided by 2 minus 0 milliseconds. M1 is 8 milliamps per second. 8 milliamps per second. Current I is 8 to 10 raised to minus 3 times T. This is, of course, Y equals mx plus b. B is 0, x is t, y is I, and m slope is 0.008. So I have my expression for I in the first time period. Okay, simply describing the slope. This time I do have to write out the expression because I need to integrate it. I can't just do the slope. If you look at the second time period, it's a flat line. It's not a function of time. The value doesn't change with respect to time. It's a flat line. You simply write out the value, minus 8 microamps. That's it. Constant value. We'll simply integrate the constant. All right, move ahead. So now, limits of the integral. This is going to be very important. For time period T1, we are going from 0 to 2. So T0, meaning the point in time where I begin my analysis, is 0 milliseconds. And T, when I end it, is 2 milliseconds. But I want my answer to be a function of time, right? If I wish to calculate the value of the voltage at, let's say, 0.3 milliseconds, then I need an expression, I need an equation where I can plug in that value. So my final answer should be as a function of time. So the limits of the integral will also be t. I will integrate from 0 to t. Does that make sense to everyone? Right? 0 to t. So let's see. Also in this case, we are starting at time t equal to 0, and the value of the previous current before time t equal to 0 was 0, meaning there is no stored energy in that capacitor. If there is no stored energy, it means voltage at time t equal to 0 is 0 volts. Voltage at t0 is 0 volts. So my expression is, of course, voltage is 1 over C integral 0 to t for the current, and the current in the first time period is given by the expression 8 into 10 raised to minus 3 t dt. Now my variable is t and my limit is also t. So to avoid confusion, typically what we do is we simply change the t to x. Change. But this sometimes ends up causing even more confusion. So again, I want to be clear. The variable in the equation is t and the limit is also t. So once you solve this, capacitor value is 4 microfarads. So 4 into 10 raised to minus 6, integral 0 to t. I'm sorry, we already did that. 8 into 10 raised to minus 3 x dx. We bring that outside. Where did that go? So 8 into 10 raised to minus 3. Get x squared or t squared over 2. And my limit is 0 to t. Plug in the value and I obtain 10 cubed t squared. 10 cubed times t squared. It's a function of time. Okay, how much time left? 7 minutes left. So we have time to cover. 10 cubed t squared. Again, less about circuit analysis, mostly just about math. When we get to the second time period, what will happen? The current was being applied between 0 and 2. So there is voltage across that capacitor at the end of the first time period, meaning when 2 milliseconds comes around, there is some stored energy in that capacitor. And we have to add that stored energy into our equation. For the first time period, that initial stored energy was 0 volts. The second time period, it is not 0. We have to determine what that energy is by plugging in t equals 2 milliseconds in the equation we derived for t1. So the equation that we derive for t1, initial stored energy for, not initial, sorry. Energy stored at the end, meaning at t equals 2 milliseconds, you plug in voltage at time t equals 2 milliseconds. and you obtain the answer as 4 millivolts. 4 millivolts. Does that make sense to everyone? Right. This is the initial stored energy. So this is the ending energy at the end of the first time period, but it is the beginning or the stored energy at the beginning of the second time period. And this is where we add that stored energy into the equation. So that value is 4 millivolts, and we will add that in this equation. Okay, so the expression remains the same, but this time our job is a little easier because the value of the current is simply a constant, right? X dx, integrate the constant, you simply get the variable. So for time t2, my t0, initial starting point of my analysis is 2 milliseconds. And that's why we found V0 is equal to voltage at time t equals to 2 milliseconds, which we found as 4 millivolts in the previous slide. Okay. Now we plug in the value. Voltage is 1 over C integral of the current I. Limits of the integral are T0 to T. And so voltage is 8 into 10 raised to minus 6 divided by 4 into 10 raised to minus 6. Beginning point is 2 milliseconds, end point is simply the variable t. Plug in the value, and you obtain the expression that is shown here. Minus 2t plus 8 into 10 raised to minus 3 volts. All right, let's take a pause. Let me know if you have any questions. Any questions? Yes. Sorry, could you repeat that, please? Yeah, IC is simply the capacitor current. That's it. Sometimes we use the subscript, sometimes we don't. So I kept it on there on purpose just to show students, that it's the same. Previously, I used to just talk about it, but then students would end up using, but then I started putting it in there so that students can actually see that it doesn't make a difference if it's just I or IC or I of T or IC of T. They all mean exactly the same thing. We do want to specify it's IC of T. C doesn't matter because it's only one capacitor in that entire problem, right? So C, the subscript C doesn't actually matter. But function of time does indicate, it's I of T. It's time dependent. So even if it's not there, students should understand that it is a function of time. Okay, it is a function of time. Okay. So before we had programmable calculators and computers and spreadsheets, we used to plot this manually, right? So we had an expression, the function of time, we would plug in t is equal to 0.1, 0.2, 0.3, calculate the value of that expression, and then plot it out. So individual dots. That's how we used to do it, right? You can still do that, of course. You can take a spreadsheet, program the equation in there, program values of t. It will give you a bunch of values for the voltage. You can plot it out. This is for T1. This is for T2. T1, if you remember, was 10 cubed T square. t squared, right? So for every value of t, it's squared. But t2 was simply a function of time, 8t. 2t, sorry, 2t. So you program this in MATLAB, spreadsheets, programmable calculators, online solvers, and you would obtain this kind of graph. Okay, that is the end of chapter 3. We already covered these slides. The last slide is simply a summary of all the equations that you would need. You can compare them side by side. And they all have a similar structure. You can have this as equation sheets if you want on the final. I might even make it open book. I don't know yet. But again, the equations are something I always tell students, you don't have to memorize them, but you should know, you should understand them. You should know how to use and apply them. That's the more important part. Okay. So I'll be in my office later this afternoon. If you have any questions, stop by, come see me, send me an email. I can meet over Zoom. Otherwise, I'll bid you a good day, and I will see you all on Friday when we begin chapter 4.